Welcome to the Embedded Systems App of the Day. What is that? Let's see if we can show one side. There it is. What does that look like now from that side? All right, so that's one of those laptop plugs, sockets, right? So then if we go like that, what is that? That's a small hard drive. So what this is it's an IBM/Hitachi hard drive for additional storage. I believe, but I'm not positive, so let me see if I can read on this what it is. This is a whopping 8 gigabytes, all right? So for a 8 gig hard drive, that's pretty darn good, right? Or is it? Considering that this is about 10 years old, it's probably pretty good for its time. By the way, the top surface is not its actual surface, it's a piece of plastic that we cut out and put on top of it. So the whole idea of this is that it is an entire embedded system, because we have some way, using these pins, to communicate with this entire device. We have these chips, and let's see if I could zoom in on maybe these chips in particular. We have some chips here, and I'm not really sure who the manufacturer is. Looks like M, that might be Mitsubishi, but this little thing in the corner says Japan. And I don't know which one this is. I probably should have looked this up so I could see. But the whole idea is that you have a small embedded system which specifically is designed to work with this mechanical hard drive. Now, 10 years ago, flash sizes, remember the USB thumb drives you used to get as little giveaways? They had how much storage space on them?
512.
I'm even going back further, 4 meg. And then they went up to 16 meg, and then they got 512 meg, and now they're up to 64 gig at least. In fact, 64 gig, is that the sweet spot now, or is it still 16? It's just amazing what you can store. By the way, you do realize that, I'll have to show historical pictures on all of this. When you're talking about a thumb drive with 16 gigabytes, you now are representing pretty much all of the hard disk storage space available in the world in about 1960. In the world. And I might be exaggerating a bit. It might be a little bit later. It might be 1964. But the whole concept is that the amount of storage space is accelerating, and as we create more and more data, not necessarily more and more knowledge, but more and more data. So this is a device that you could put into your laptop to get you some additional storage space if you wanted to switch it between different machines. This predates USB thumb drives, and this is another one of our embedded systems apps of the day.
How much was it at that time?
I gotta believe it's somewhere around $200. And this was given to me by Bill Haybrook, who used to work at IBM's local plant, and later Hitachi, and they're the ones who did that. All right? That being it, thank you very much. Welcome to Embedded Systems. We are going to talk today about, by the way, this is lecture 12. We're going to talk about data communications. So how many of you have communicated serially? All right. How many of you have a thumb drive, a USB key or a USB drive that you've ever used in your life? Ever. All right?
Using one now.
Yeah, some people are not raising their hand. Is that because you're angry? You just got your arms folded? You've never used a thumb drive, but a USB? All right. Those are all examples of serial communications. You're transmitting stuff one at a time, or one bit at a time. So today we're going to go into a little bit of detail about this. Oh, by the way, I got some new stuff for the prize closet. One of them includes a squishy ball, which I get to throw at people who are putting their heads down and sleeping.
I get free squishy balls.
Free squishy ball is good. You didn't hit him hard enough to hit the guy next to him, all right? So, must be a rough week. All right. So, the whole idea of serial communications is that it's relatively inexpensive. Think about this. If you want to communicate really fast and lots of data, you can do it in a parallel fashion. And in fact, that's what you do with memory. For example, let's see, 1, 2, 3, 4, 5, 6, 7, I'll even do 8. So if you have simply a CPU and you have a memory, you can communicate with your memory in a parallel fashion, a lot of bits at one time. But you know what? You could also communicate with some memory using only a couple of lines, a couple of bits at a time. And that needs some special coordination. Well, both of them need some coordination. Both of them usually require on having some sort of synchronicity or synchronous clock or some other signals. So in this case, with our memory that we're doing serially, we're going to have to rely on some sort of clock. And so this clock is going to be the way to keep both of them aligned and in sync. So let's take a look at here I am writing all this stuff on it, and I was still zoomed in. So let's take a look, and by the way, for those of you following in TV land, and many of you do, I'll just include this right now and draw it later. For those of you who want to follow along on your computers, I actually have, this is the data specifically, and this thing still has high gain. Serial communications. If you look at one of the previous versions of the course, this is the same file. Is this really loud for you guys?
No, you did.
All right. Just don't start yelling, right? Or throwing squishy balls.
I'll try to contain myself.
You know, Mr. Lawless, if you really wanted this, you should pretend you're sleeping. and then I could throw it.
And I can see like myself.
You are Charles, right?
Yeah.
Oh, okay. You're looking at me really funny. So, in lecture number 12, 13, and likely 14 and 15, but I'm not sure exactly how many of these, I'm going to be talking about all concepts associated with this. Now, I'm going to start with the general concepts. How many of you, all right, here's the poll. You have to answer one of these, all right, because I got to judge how to do the lecture. How many of you You're still recording, right?
Well, I'm just making sure that everything's still in the frame.
Oh, okay. How many of you, you have a choice of three things? You know a lot about serial communications, you know enough to make it dangerous, and you have absolutely no clue about how that goes on, all right? So how many of you are an expert at serial communications? All right, be brave, raise your hand.
I'm an expert.
All right, I'm going to have you teach your class then. You ready? Yeah, you will do that, all right? All right, how many of you you have enough knowledge to make you dangerous? All right? How many of you have absolutely no clue? All right, so I'm going to... He doesn't know? He didn't vote? Where's that squishy ball? So, rather than pulling somebody up and embarrassing you, and kind of like I did with the let's guess a maybe I should do it. Nah, I won't do it this time. Let's go over a little bit of background. We're going to talk about RS-232. It's a really easy one to understand. It's also a nice one to explain all the aspects of serial communications, both from a hardware and a software standpoint. We'll talk about UART in general, poll code, and we're not going to look at interrupts yet. That comes up in a future lecture. And then we'll look at some other standards like SCSI and I2C, which are predominantly used in the industry for communicating serially to other devices. So I'll probably start that out by saying the following. Ooh, look at this. I get close, it goes nuts. Imagine you have a whole bunch of devices. And this is your main microcontroller. Oh yeah, you can see it. Sorry. And let's say you have an accelerometer. Let's say you have memory. Let's say you have, what's one of our other devices? That's I2C, I'm trying to remember. Any hints? Well, let's say we have another device. And I'll try and remember which ones are I2C on our board. Now, remember how I said up here, you can do it many bits at a time? And this is parallel. Or you can do it like a couple at a time. And this is more like serial. Now, what's one of the problems of doing it parallel to everything? You got a lot of wires, right? Wires are also known as what? Antennas, right? And also the opportunity for loss because there's all sorts of stuff hanging off of it. So often, and they take up a lot of space. That's the biggest thing too. So maybe you want to do just a couple of wires. And so what you can do is you can say, well, I'm going to talk to everybody on the same wire. And so you have to have some standard by which you talk to all these different devices on one wire. It might be more, it might be maybe a total of 3 wires. And so what we're going to see later is a technology where we are able to talk serially using something like I2C. And each one of these devices can be attached to the exact same wires. And what that does is it frees up a lot of the pins going into your microcontroller to be either not connected or to have some other functions. Because in most microcontrollers that are relatively small, you have only a limited number of wires that go in or out. So that's going to be our basis for taking a look at serial communications. So let's go into the transparencies and take a look at more detail. First of all, we have to take a look at data communications in general and what it is. So a while ago, in the early days of computing, there were no standards whatsoever for anything. In fact, that's why you see little endian and big endian, is because people just do things differently. And so the International Organization for Standardization, ISO, it's not IOS, it's ISO, because actually, if you look at it in French, which I think where the name comes from, they created what's considered the Open Systems Interconnect Reference Model, where communications is handled in such a way that different functionality is given a different layer. And so all the way at the bottom is what we call the physical layer, and that's the actual transmission of the electrical bits and bytes. Specifically, I'm sending out 5 volts. Specifically, 0 volts is assumed to be ground, or plus and minus 10 volts, or some other type of standard, whatever you identify. And the ISO didn't say that you had to send at a certain voltage or so. It just said that that's where the definition is comprised, in that layers number 1. Then comes the data link layer, network transport session presentation, all the way up to the application that is going to be using the data. Now, not necessarily every computing device has all 7 layers, and in fact, some computing devices, for example, routers, are only running layers 1 through 4, because all they do is they take information and they pass it along. They don't actually consume it like an application. But in our case, we're going to concentrate mostly on the physical layer and a little bit on the data link layer until we get later in the lecture, where we're going to talk about some applications that are going to use the data from serial communications. And you'll see how this all works. So, physical layer, serial communications, again, we're just relying on, in this case, a 2-wire communications. 2-wire means 1 wire is for transmit, and the second wire is for receive. Now, the one thing you don't see here is what? All right, clock and, or acknowledge, but probably more importantly, ground. So very often when you have 2 devices that are communicating, you want to have a common ground. That way you can identify what really is for your voltage level a 1 versus a 0. Now, here's where it depends on the specific protocol and the specific communications standard that you're using. You're basically sending 1s and 0s. What's the voltage of 1 and what's the voltage of 0? All right, the answer is depends. Depends on your standard. Because the communications for 802.11, or what's the standard for Ethernet? Is it 802.3 or something like that? I forget what it is. But the standard for 802.3, which I think is Ethernet, and RS-232 is completely different. It's also different for RS-485. So it all depends on specifically what you want to do. In fact, it's even different for the CAN bus. There's all sorts of different serial communications standards. But the main thing you have to remember, and this is the basics, so as long as you understand the basics, you're in good shape, is, hey, you need a ground reference somehow, and you can communicate with 1 or 2 wires. So you can have the same single wire have data that goes back and forth. Or you can just say, okay, one way is going to be from one to the other, the transmit, and then the other way is going to be receiving from the other device. Now I'm going to talk about this simple device as only between, or the simple communications examples between 2 devices. So we're not going to hang anything else off. And then what we really care about is the data is sent from one place to another. And again, I'm going to talk about the basics of this, of serial communications, and then later on, we're just going to say that the communications method is going to be some sort of black box that we just shove data into, and then data occurs. So at this point, we're going to take a look at really great detail on this. And as soon as you understand that, it's going to turn out eventually that our microcontroller is going to be nothing more than, here is a register that you put data in. You put a byte into that register, and then maybe later you'll go and you'll get a byte from there. And then the hardware takes care of everything. You don't care how the hardware does it. Because the nice thing about microcontrollers is, in our microcontroller, it handles how to send out one bit at a time, what voltage it has to be, the timing, and everything else like that. So let's take a look at some of the detail about how we're going to do that. So, in our basics, for something like RS-232, we have several agreements that we need to make between our two devices, the sending and receiving ones. And some of the things that you have to agree on is the following. How much data are you going to send? Is the data going to be 6 bits, 7 bits, 8 bits, or 9 bits, for example? And how you're going to identify that you're going to start transmission, how you're going to identify when you have finished transmission, stop it, if you're going to have any error detection or error correction, how fast you're going to spend or send this data. So let's take a look at some of the basics here. We'll want to send a single bit, and it's not a good data bit, it's just a start bit that says, I'm about to send you really good data. Because before that, the specific line was held at a certain state. In this case, in RS-232, it will be held at the 1 state. In other words, logical 1, whatever that turns out to be, whatever voltage. And it will be held there until you lower it down, in which it says, I'm going to start communications. Then, at a certain amount of time later, our first bit is available, then our second, then our third, then our fourth, then our fifth, then our sixth, then our seventh, then our eighth. And then we're going to add in here some error detection and correction. Then we will follow that up with a stop bit, meaning that we'll bring up our communications line back up to 1, logical 1, for at least one time period. Now, this is going to be synchronous communications. I'm sorry. It will be asynchronous communications, but it will have definite timing because it's just hardware. It's going to read what the voltage is. Once it sees this falling edge, it'll then say, what is the voltage in the middle of this, and be able to get the data in there. You have to, in advance, agree to what speed you're going to send it in. This is 300 bits per second, and that's pretty slow. 200 bits per second. You know, what's USB transmitting at? What's USB 1.0 transmitting at? I can't remember. Was that 5 megabits per second? And then USB 2.0 went up to 10 or something like that. And now we're at 3.0 or 4.0? 3.0 or 3 what? 3 what? 3.0, and what is that speed? Something obnoxiously fast, right? Yeah, back in the old days when I was just a young kid hacking at computers in the late 70s, I thought I was really cool for having serial communications that was running at 120 bits per second. That's not 1,000, 120 bits per second, and I was happy. And my mom was really ticked off at me because I would tie up the phone line, because that's how we communicated, is with the phone line. And only the phone line. Now, I'm really ticked off because my in-house cable is only running at 50 megabits per second. Poor me. All right, so, again, if we are working with this, the first start bit will be followed by your data bits, whatever you define, parity, and then the stop bit at the end. Now keep in mind that what you store in these data bits is going to be something that is determined at a higher level of our OSI model. Right now we're just worrying about physical layer number 1. So, let's see if I actually look at an example of it. Let's look at a quick example to exercise our brain. So if we look at, let's say I want to send a byte hex A5. By the way, what is the binary representation of that? All right? So I said, before we do this, we have to agree on what is going to be the speed that I send this at. What is going to be the number of stop bits? This is, we're communicating between two different devices. We have to identify if we're going to have some parity. This is error detection correction. So in our case, let's see, we'll call this odd parity. Odd parity means I need an odd number of bits here at all times. So in this case, I have how many bits? 1, 2, 3, 4. 4 1 bits, right? So if I say I need an odd number of bits, that means in this case, my parity is going to be equal to 1. And by the way, I'm going to say the number of stop bits is going to be equal to 1 bit. So what I would transmit is as follows. I would be up here, 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 and then all of a sudden, wall. This is my start bit. Then I would start transmitting data. And in this case, I'm going to send it most significant bits first. So the first bit I'm going to send is going to be a 1. Then I'm going to send a 0. Then I'm going to send a 1. Then I'm going to send a 0. Then I'm going to send a 0. Then I'm going to send a 1. Then I'm going to send a 0. Then I'm going to send a 1. What comes next according to what I said earlier? My parity bit, right? So my parity bit is going to be 1 as well. And then I'm going to send a stop bit. And what's my stop bit? My stop bit is also going to be 1. So what it turns out is between this time and this time, I've sent a total of how many bits? We have 8 data bits, right? 1 start, 1 parity, 1 stop. That's a total of 11 bits. Which means we have some sort of overhead. Overhead meaning I have 3 bits. 3 extra bits that's not real data. So, what I would like you to do, since I've been talking for this whole time, and it's time for you to actually do some exercise. Yeah, here you are. So, show me what the waveform is going to be like, and turn to your neighbor and do that. In here, see if I can make it.
Restart?
So, let's say I want to send the data $53, $21, 2F. I'm going to have even parity. I'm going to have one stop bit. By the way, in our model, we send only one byte at a time, right? So in my example here, if I wanted to send something else, I would immediately have to say, here's my next start bit. So I just can't send 16 bits at one time. So with that in mind, what is it going to look like if this is my data, even parity one stop bit? So go ahead and show me what the wave will look like, and we'll see what you have. This is for a trip to the prize closet. Somebody draw me a nice neat picture for the trip to the prize closet. If you could pause. Charles. All right, we have a winner.
Oh, Jim.
He was selected because he's got a cool device. Except there's like a big giant light that comes down from all top. Cool. So here we go. Stop bit, yes, it goes to 0. And 0, 1, 0, 1, that looks good. 0, 0, 1, 1, yeah, that looks good. Then the parity, remember we need an odd number of bytes or bits. We need a, oh, did I say? I said even number of bits, sorry. Then one stop bit, then start bit again. 0, yep, looks good. Parity is 1 and stop bit. Yeah, I think that looks good. What do you think?
Give him another trip to the prize closet.
And again, for those of you who are interested in having your work selected, having a cool device like this will let you in. So, as I said, what's Samsung today? We have no idea what that was. Yes. All right, so if you were to see something like that on your test, would you know what that is? Yes. Now here comes the question. How long does it take, or what is the throughput of that? How long does it take it to send it? So with that data, how long does it take to send? The answer is what? All right, so 22 clocks. So how fast is that? It depends on what your clock is, right? I didn't say how fast the communications was. So if our communications was 4,800 bits per second, how long is that? Okay, here's your math, right? 4,800 bits per second. So if we have 22 bits, and we're multiplying it by 1 over 4,800 bits per second. Is that right? Yeah, bits per second. Which means 1 second is equal to 4,800 bits. Where's my people with the calculator?
4.58.
Is what?
4.58.
4.58 what? Okay, 1 second. 0 point what? 0.004. Is that right? not agree with that? All right. So this is going to be a pretty typical thing to have to worry about. So you'll never know when you'll find something like that on a test. It is almost time for me to finish, so let me see if there's anything else I need to cover today. So I think that's all I want to cover today. So, peace out, and I'll see you on Wednesday.